We'll start out Module 2 by looking at Chapter 1, where we address some philosophical issues and fundamental concepts in environmental engineering. We'll start out with this pretty picture of a coral reef, and you might be wondering, what does this have to do with environmental geology? And what its significance is as Earth's system begins to experience fluctuations, and we don't need to talk about whether those fluctuations are good things or bad things, but as change occurs, we need to be able to find the most sensitive spots on Earth in order to be able to monitor that change, understand whether a change is significant or not. And one of those most sensitive places to changes in Earth systems are coral reefs, where the abundant lush life at these coral reefs are highly dependent on the particular conditions present at that location. So as conditions change, the coral reef areas might be one of the places that are best indicators that change is occurring. And you can look at some of the coral reefs, for example, in the Great Barrier Reef off Australia, to recognize that massive changes are occurring on Earth's surface right now. Another place where you might be able to look for sensitivities is how Earth's system is impacting humanity. And after the 2010 earthquake in Haiti, this is a temporary housing that people were forced to rely on in that situation, because that population, humanity, wasn't prepared to be able to withstand Earth's changes and maintain the housing standards that we've grown accustomed to. When we look at Earth's place in space, we have to recognize that Earth is geospatially isolated within the universe. We don't have a near cousin that we can look to for examples of how our Earth system might evolve, nor can we look at a sister planet as a potential location for humanity to see its future in having our population thrive on a nearby planet instead of the one we've got. The one we've got is the one we've got. The universe began with a big bang, and at least in this cycle, all systems have been evolving from that process. When Earth was created, it wasn't in its original configuration. It was gaseous originally, and then it was fairly uniform, but later Earth developed as a system of different layers and potential systems within that system, and we developed a lithosphere, an atmosphere, a hydrosphere, and a biosphere most recently. One of the realities is that we're facing limited resources. We only have the resources available to us on Earth's surface that we have. And whether those resources are energy resources, the soil that we use for agricultural purposes, whether it's fresh water we use for drinking or for agriculture, whether it's forests that we use to help sustain our atmosphere or other uses of forest materials, ocean fisheries are also limited, and we've seen over the recent centuries how fisheries certainly have changed, and rangelands might be an example of another resource that is facing the reality that we only have so much land of that type. While we have local and regional environmental interests, we also have global environmental concerns, and one of the problems is that at every level, whether it's local, regional, national, or globally, we always have conflicts, and we need to look at integrated resolutions to the competing interests and the competing needs for various portions of Earth's resources. Inception began about 4.6 billion years ago with the Big Bang, and the Earth as a system evolved very gradually at first, and very recently life emerged on Earth's surface, and most recently of all, you'll see in Figure 1A that human beings began to populate Earth's surface. Let's continue now looking at the definition of environmental geology. Environmental geology is applied geology that's focused on the environmental issues involving geologic materials. What's the value of knowledge of environmental geology? Well, to better understand environmental problems, we need geologic knowledge for two kinds of problem solving. First, to minimize environmental degradation, and second, to optimize the use of resources to maximize the environmental benefits for society. I'm going to look at 5 different concepts in the fundamental concepts that we need to consider in this course. One thing I'd like to point out is, particularly in chapter 1 and 2, I'm not giving long lectures. I do expect you to be able to read those chapters to get a lot more material. And when reading this textbook, recognize that you'll need to go into many of the figures, many of the closer looks that are associated with some of the figures, or special case studies that are within the chapter. So be sure to read all of the chapter. But I'm going to briefly try and outline 5 fundamental concepts from chapter 1 here. And those are population growth, define sustainability and consider what it would involve, look at the concept of systems and change, to look at hazardous earth processes, and finally to define what scientific knowledge and values are. Another important concept is in environmental geology is to recognize that while facing finite resources on Earth, we have to recognize or give some regard to our obligation to the future. For those of us who have no children, we may not feel compelled to give any regard to future generations. But for those of us who are going to have offspring and consider future generations, then our obligations to them are partly a matter of personal ethics and a personal choice. But we collectively have the responsibility that we have to future obligations, and we'll all decide that together. That first issue is human population growth. It's the number one environmental problem on Earth. There are nearly 7 billion people on Earth by 2010. Your book talks about a population bomb, and I'll describe more about that in a minute. But it results of the fact that we're experiencing exponential growth, consistently and constantly growing. To understand what exponential growth is, you might be more familiar with it in terms of earnings on income or mortgage rates. But and when we look at population growth, we might look at the growth rate, and if we call that G, that's measured as a percentage. If we want to know what the doubling time is for the population, we would just say the doubling time, D, is equal to 70 divided by that growth rate, G. And with that, we get our doubling time. You can use the same calculation in calculating how much interest you'll earn on a bank account that you leave alone for decades. But when we consider the human population growth, we can use the same formula. Our current population is above Earth's comfortable carrying capacity. That means we continue to use more resources, and as we have more people on Earth's surface, then we need more land space, and we generate more waste and further degrade our we further degrade Earth's carrying capacity and ability to sustain life for future generations. While we might be fans of science fiction, and I am for one, we must recognize that Earth is the only suitable habitat for future generations for the foreseeable future. Look at this picture and wonder how this might relate to the population bomb. Is this some sort of CGI post-apocalyptic image of what life might be like at some point in the future? No, it's from the 80s. It's from Ethiopia, after the region had been subjected to famine for a number of years, and there was massive impact on the population and extensive death and great suffering. when we look at the population growth, and this image is a useful one to consider the concept of the population bomb, as you can see the Earth's population in 1830 at about 1 billion, growing recently to about 7 billion. What we'd like to do in the next few slides is to consider different countries that are experiencing different kinds of growth and therefore are experiencing the population bomb quite differently. So looking next at the first two of our four countries in the next slide. I'm going to be comparing four different countries that are experiencing very different. First one is Kenya, where we see that it's experiencing massive growth, about 2.65% growth rate per year. And that means the population will double in just 26 years. The next country we're going to consider is Haiti. And Haiti is experiencing population growth of 1.58 per year, which gives us a doubling time of 44 years. The United States is experiencing a growth rate of 0.9% per year, which means that we can expect our population to double in about 72 years. Italy, on the other hand, is experiencing a negative 0.5% growth, so their population numbers are actually declining, and on an annual basis, and so their population is gradually decreasing, and it's probably too risky to try and predict the rate at which it might be shrinking in future decades. The other part of this image that I'd like you to consider is shown with this histogram of different age distributions. So the age distribution is shown for each of those four countries, and one of the things to note is in those countries experiencing the most rapid growth rate, we see that it's actually the children make up the largest portion, or actually are present in the highest numbers within those populations. And because of that reality, it's one of the things that contributes to our expectations that both countries will continue to experience rapid growth rate. In the United States, our population distribution across different age categories is much more uniform, which means that we're probably in a situation to be able to have a more sustained growth rate, or I should say, to have a more consistent growth rate in future decades. In Italy, by contrast, we see that in the youngest populations, we actually have some of the smallest numbers of Italian residents. So that's one of the reasons that it's anticipated that population numbers will continue to decline in Italy. The thing I want to say about human population growth is to recognize that we're going to have uneven growing pace and distribution. By 2050, we're going to have 3 billion more people on Earth, which means we'll get up to about 10 billion people. Almost all of that growth is occurring in developing countries. Not only developing countries, but most of that growth is within developing countries. There's really no easy answer to the population problem or solving this population bomb, but if the past is any indicator, then education is paramount to coming to deal with it or reducing the impact of the population growth. Especially women's education seems to be critical for managing a country's growth rate. As people become more educated, the population growth rate tends to decrease. If there's any good news in recent data, it's that the rate of population growth is decreasing. Population is still increasing, but is not growing as fast in recent years as it had been, say, a decade ago. The next concept in Chapter 1 we're going to take up is to look at sustainability. Sustainability is an environmental objective. it's an evolving concept, and everybody's definition of what is meant by sustainable will be different. There's our expectation of what we'd like to see in a sustainable system and the reality of what we're actually able to achieve or what's actually needed in order to meet sustainability definitions. The criteria for sustainability vary in space and over time. Voters in our municipalities and our regions define what kind of sustainability goals we may have, and 20 years from now, those voters might have a very different interpretation. What is defined as sustainable in California, say, might be very different than what is defined as sustainable in a mining town in Montana. Sustainability is a long-term concept, and it has long-term implications. Longer than our lifetimes is typically what's needed to understand sustainability, because we bring in concepts of intergenerational fairness. Sustainability requires careful resource allocation, large-scale development of new technology for resource use, and recycling and disposable and waste disposal. And all issues within sustainability are a matter of choice, how we're going to choose to live and what kind of impact we're willing to have on future generations. The issue in sustainability is, how do we measure it? There's no common agreement on how do you measure or quantify sustainability. It would certainly involve use and consumption of non-renewable resources. If we use up all the coal, then we're not leaving any coal as an option for future generations. If we use up all the hydrocarbons near Earth's surface, then we're not allowing future generations to have access to that type of or that category of resources. We'll have the natural replenishment of renewal rates for some resources, such as biofuels, but there are other resources that are simply not renewable and for which there is no replenishment. Even though oil occurs as a result of natural processes, those processes are going to turn out to be so slow that we certainly can't regard that as a renewable resource. Another thing to consider when measuring sustainability is that we can look at global consumption versus replenishment of resources. So it's not just at a regional level. We might want to make our measurements at a global scale. Also, we might have development and improvement of human environment versus what is a viable environment. So while life might be sustainable at some point in the future, we might want it to use resources now at a rate that makes it so that future environments are only barely survivable. And it's partly a matter of choice, the choices we make every day. And another way of measuring sustainability is that most definitions of sustainability would involve elimination of environmental crises. So we don't want any use of resources to lead to environmental crisis if our goal is sustainability. The next major concept we'll consider is systems. And if we look at Earth's systems and changes in those systems, we need to recognize that Earth is a dynamic system. It's got many components and it's changing. We could consider 4 interconnected subsystems within Earth's systems involving the lithosphere, the Earth, the crust, the atmosphere, what we breathe, the hydrosphere, the water content, and the biosphere, the living component of Earth's surface. These 4 subsystems are interconnected and very much interdependent. And lastly, the concept of looking at change, we need to recognize that present human activity is our key to understanding the future. More specifics on that focus on human activity as for understanding the future, let's look at some geologic concepts. Some of the geologic concepts we need to consider are first uniformitarianism. The basic concept in this geologic principle is that the present is key to understanding the past. If we want to understand how coral reefs might have operated in the past, we can go study coral reefs today. But also, the present is key to the future. If we want to understand how coral reefs might be changing in the future, we should look at how they're changing now. We also need to recognize that whatever rates are occurring on Earth, any changes in frequency and magnitude may result as a consequence of geologic processes or human activities. And there are a number of geologic processes that can have a global impact on the Earth system, and there are a number of human activities that can also have a global impact on Earth systems. Next concept is environmental unity, and this is something of a philosophy, but it also is tied to a reality in that there's a interconnectedness that means that there's a chain of actions and reactions in any perturbation in Earth's system, in any disruption or alteration of Earth systems. So by looking at that interconnectedness, we can also philosophically see an environmental unity to Earth system. The last concept in Earth system that some people find useful is a Gaia hypothesis, which is really a philosophy that regards Earth as a living organism. Now, Earth is not a living organism. It isn't. But it has some characteristics that might mimic a living organism. It has complex and interconnected subsystems, and the concept of the Gaia hypothesis is something that some people find useful when considering a global perspective on the environment. The next big concept we want to consider is hazardous Earth processes. Hazardous Earth processes and risk statistics for the last 2 decades show an annual loss of life of around 150,000, a financial loss on an annual basis of over 20 billion. Millions of lives are lost in the last 20 years as a result of major natural disasters in developing countries. There was a 2003 earthquake in Iran where 30,000 people died. In 2004, there were tsunamis in Asia that killed more than 300,000 people. And more property damage tends to occur in the more developed countries, whereas loss of life tends to be more catastrophic in the developing countries. Another thing I'd like to mention is about hazardous Earth processes is what we're not covering. In fact, a large portion of your textbook addresses hazardous Earth processes, naturally occurring processes such as volcanic eruptions and earthquakes. And these are concepts most traditionally covered in a conventional course on geology. So we're going to focus on chapters and concepts that are more consistent with a look at environmental geology. Next, I'd like to look at some fundamental concepts in science and solving problems using the scientific method. Science might be regarded as an accumulation of knowledge and knowledge that we can use as a basis for decision making. If we apply scientific methods to environmental problems, then we might be able to formulate possible solutions to those problems. If we look at the scientific design of our decision making, we might be able to find a structure for those decisions that create a more suitable, that are more suitable for certainty. Environmental issues, let's remember that we're going to be looking at the accumulated scientific knowledge that comes from the application of the scientific method. I expect all of you are familiar with the scientific method, but figure 1.14 describes the process, how hypotheses could be subjected to testing, and based on the outcome of the testing can either lead to a refinement of the hypothesis, an acceptance of the hypothesis, or a rejection of the hypothesis. And as we add related hypotheses, and those hypotheses become more firmly entrenched, we can develop theories. And we bring our collection of theories and hypotheses with us over time to create our accumulated scientific knowledge. Lastly, I'd like to look at the challenge of solving environmental problems. These are difficult processes to understand and to characterize. Environmental problems tend to be very complex with no easy answers. Environmental problems often involve rapid changes, but slow recognition of the problems and slower actions or reactions in an attempt to solve those problems. Some changes are of an irreversible nature. If a particular species is driven extinct, it's gone. There's no changing that. If we have non-renewable resources that we use up, they're gone. We can't change that and undo that step. Environmental policy links to environmental economics is in its infancy, so we only begin to understand how to try and motivate change in people's behavior that will have an impact on our environmental reality. The last concept I'd like to look at is to examine the precautionary principle. It's a possible public policy philosophy that you may or may not find useful. Other people do adopt it, so it's useful to know what the precautionary principle is. It's a principle that recognizes that, or believes that, scientific certainty would not need to be required in order to take a precautionary approach and make a change. So if something may be causing harm, it would be best to try and stop that thing that may be causing harm under a precautionary principle. They don't require certain proof that it's causing harm. Part of the reality behind why people might be an advocate for the precautionary principle is that scientific proof is not possible in dealing with many environmental problems. The precautionary principle may be difficult to apply, partly because our state of knowing, but another reason why the precautionary principle is difficult to apply is because not everybody in a region or globally is going to be in agreement on being even advocates for the precautionary principle, let alone interpreters of the same data set. The adoption of the precautionary principle may lead to a proactive approach with an emphasis on environmental unity, and you can read more about that in Chapter 1 of your textbook. See you in the next chapter.